Our first set of ranking tasks. We'll probably have, I don't know, maybe 3 more packets between now and the end of the quarter of these ranking tasks. These are just so excellent, I think, for E&M. And one of the things that I have found over the years is that even students that come into the class with a fair amount of circuits background, they are able to find gaps in their conceptual understanding in these packets. And we're able to figure that out. So, these are a great place to start, whether you have a ton of experience in circuits. I would say still go through here and make sure that you're pretty solid as far as your understanding goes. Okay, so getting started with this first one. This first one asks us to rank from brightest to least bright on the basis of how bright the bulb is. And I can relate this bulb brightness right here to potential difference. So right away, I'm going to relate that to the potential difference over the bulb. I can call that V sub B. I'll write bulb here to make that really clear. So when I look at the situation, we're told here that all the batteries are identical. So I can let all the batteries have a potential difference E, right? Just so I can quantify this a little bit. And then I can go through and I can actually write out what is the potential difference across each of these light bulbs. And then I can rank it that way. So in case A, this light bulb is just wired directly to this battery. The potential difference over this bulb is just going to be E. It has one potential difference of this one battery across it. If I look at case B now, I see that there are 2 batteries wired in series. So this is like 2 staircases in series. You go up one flight of E, another flight of E. So that makes a total potential difference of 2E over this battery. So you got to be kind of thinking about, you can think about it in terms of loop rule, but really all loop rule is just applying this idea of potential as elevation around your circuit, right? That's really all that's going on there. So here again, at this first battery here, I go up from 0 to E, right? And then the second battery, I go up from E to 2E there. All right. For case C, I have 3 batteries in series. So of course, my potential difference over this light bulb is going to be 3E. Now in case D, I have 2 batteries in parallel. So this is two flights of stairs that are next to each other, not one after the other, but like in a big building or something, 2 sets of stairs that are next to each other. So both of those sets of stairs matter, right? But they don't get you to the second floor. You're only able to traverse from one floor. So this is still only a potential difference of E. This light bulb is still wired from the low side of the battery here, which we could call 0, to the high side of these 2, which we can call E. So the potential difference is still just E for that particular light bulb. And then this final case is the same, and I could wire 100 batteries here in parallel. In parallel, but this light bulb is still just going to have potential difference E across it. So if I rank here, I see that case C is the greatest with 3E. Case B comes next. And then cases A, D, and E are all the same. All right, moving on. So here we have just really simple circuits, and we're told here all the resistors in the circuits are identical. The batteries are ideal with voltages of 12 volts, and rather than using that numeric value, I'm going to just use E here, right? We want to get used to symbolic stuff anyway. That's what you're going to see from me on the next exam. So 12 is arbitrary, right? Let's just put that as E. Wires have negligible resistance, sure. Rank these on how hard it will be for the battery to drive current through each circuit from greatest to least. Circle any ties, fine. So really what this is about is equivalent resistance, right? The greater the equivalent resistance, the harder it's going to be for the battery to drive current through the circuit. So the equivalent resistance is basically the resistance. You can think about it as the resistance experienced by the battery. The battery doesn't know what the shape or like how many resistors are out there, whatever. It only knows what it experiences, which is the overall or equivalent resistance. So we're actually here going to be ranking from greatest equivalent resistance, right, to least equivalent resistance. That's what we're going to look at in each case. So let's just go through and figure that out. So we're told that the resistors are identical. I'm just going to give each resistor resistance R here then. And this is a good practice to do as you're working through these ranking tasks when you're told everything's identical, or sometimes you're given a proportional difference. Just put it in symbolic notation and work it that way. So for this first case, case A here, I can see that I have these two identical resistors in series. So my equivalent resistance here is going to be 2R. Got it. Case B, I have two resistors in parallel. And by now, this math of parallel and series should be somewhat familiar to you, right? Because we did a bunch of that last week. So here, my equivalent resistance for this case is going to be R over 2. If that doesn't make sense to you, then go back and review that. I'd stop here because that skill is a skill that you should have when you're getting to these ranking tasks. So I'd stop here, go back, work on your equivalent resistance skills, and then come back to this. Here we have three identical resistors in series. That just gives me equivalent resistance of 3R. Here we have three identical resistors in parallel for case D. That gives me equivalent resistance of R over 3. These case E is again two resistors in series. Series, remember, means same current. So 2R again here. And then case F, we have two resistors in parallel. So again, we have R over 2. So we can rank those from greatest equivalent resistance to least equivalent resistance. So the greatest is going to be then case C with 3R. And then we have case A and E are both at 2R. And then case B and F are both at R over 2. So I know I'm not circling any ties, but I'm trying to make it super clear. B and F are R over 2. And then the least equivalent resistance is case D here at R over 3. Okay, good. So these should be skills that are pretty much at your fingertips. And part of what they're trying to get at here conceptually is that you are understanding of what equivalent resistance is, right? So how hard it will be for the battery to drive current through the circuit. They want to see as the student connecting that concept to equivalent resistance, or are you taking it somewhere else? Okay. Moving on. All the resistors shown below are identical. So again, let's call those R. For notation simplicity, batteries are ideal with voltages of 6 or 12 volts. So what I'm going to do with those then, as you might imagine, is I can call those E or 2E. And I mean, it's okay to stick with the numeric values here, but again, the more you practice, the type of practice that is more like how you're going to be evaluated on the exam, the easier that's going to be for your brain at that time. So anyway, we're given the potential difference of the batteries, we're given the resistances. We don't have to worry about internal resistance in the wires. We are to rank the current passing through the upper right-hand corner of each circuit from greatest to least. Okay, this is a great question. So in figuring out current, I want you to look at each of these cases and look at the point you're being asked to analyze here. So I'm going to go to my highlighter here. Note that I'm just going to highlight these upper right-hand corner here. It's the current flowing through that point that we care about. And one of the things I want you to notice is that in all cases except B and D, right? Let me look at this again. Yeah, in all cases except B and D, it's just the same as the battery current. So you can use that fact, right? That can be useful to you. If you choose to look at it that way, there are different ways to consider this. Another way to think about, so then just finding the battery current, right? Just let me be clear about this for a second. If I am going to apply this to a battery, that gives me battery potential equals battery current times equivalent resistance. We've done some problems like that. So that can be a useful approach. It doesn't work for B and D, as I said, because in B and D, the battery current is not the current passing through the upper right-hand corner of the circuit. So you need to use a different approach there. The approach that I want to talk to you about, though, is I'm going to get rid of this here. Using potential. So for using potential, what's cool about this is in every case except F, right? F is battery current, but in all the other cases, this current point we're interested in is I can associate a resistor with that current. So what I'm trying to say is that, like, for case A, I could, in order to find the current through this point, the upper right-hand corner, I could say find the current through this resistor and it would be the same. Case B, I could find the current through this resistor, it would be the same. Case C, so case A and C, I could choose any resistor I want because they're all in series, but I'm just kind of picking one that's visually in the same spot. Case D, this is the resistor, right? Case E, either one. Case F, now I don't have a resistor in series with my point of interest. The only thing that's in series with my point of interest in the battery. So the battery is what I would have to focus on there. So you might be asking, why is she so into what's in series with her point of interest? It's because we're being asked about current. And remember how series is defined. What does series mean? Series means same current. So when you are focused on current, it's series kind of relationships that you're looking at. So the reason I bring this up is that when we look at this case, like say case A here, I can really quickly figure out what the current is through this resistor here. And that is because I'll solve here, I equals V over R, right? I know the resistance, R, that's given in this problem. And by inspection, I can find the potential drop over this resistor. How can I do that? Well, this battery, if we keep it in numeric for just a second, if this is 12 volts, these are two identical resistors, right? So if I think about loop rule going around here, I know that I'm going to drop 6 volts across this one here, halfway, and I'm going to drop 6 volts across that one there. So these two drops are going to be identical. They're identical resistors with the same amount of current going through them. So in that case, I'm looking at this relationship right here. So the potential drop over resistor is going to be, well, the product of the current going through that resistor, which is the same for these two, they're in series, multiplied by the resistance of that resistor, which is the same for these two because they're defined as being identical in the problem. So if we were to do this in symbolic form, then that would mean that I was writing this battery here as 2E, right? So that would mean that each of these resistors drops E. Okay, so the battery, you go up 2E and then you drop down E at the top resistor, you drop down E at this resistor that we're studying here. So that is a way for me to find the current for circuit A. It's going to be the potential drop over the resistor that I'm looking at, my resistor of interest, which is E, divided by its resistance, which is defined as R. All right, so I've got the current for case A. Let's do the same thing for case B. Same thing here. Again, this is 2E. This time, though, check it out. We have the drop over this resistor is the whole battery, right? The whole thing here, 2E. So I can know that because when I drop over this resistor, I go from the high side of the battery to the low side of the battery. So that means that the current for B is going to be 2E over R, twice as much as I had in case A. Let's do the same thing for C. So I'll do this, let me do it numerically first, and then we'll do it symbolically. If we're holding this as 12 volts, these three drops for these three resistors have to be identical, right? So each of these is going to drop 4 volts. And that's only the case because, again, they're all in series, so they have the same current, and we are told that they're identical, so they have the same resistance. V equal IR means they're all going to have the same drop. So I know this is a really simple case, but we've got to kind of get our feet under us with these simple cases before we can add complexity. So we're going to study simple cases first. All right, let's go back to symbolic here. This is going to be 2E. So then you know that the drop here is just going to be 2E over 3, because that potential 2E gets cut into 3 equal pieces in this case due to symmetry. So the current for case C is going to be 2E over 3R. So I'm going to kind of circle to make these stand out, these currents that I'm calculating. We can do the same thing for case D here. This 6 volts, we're calling this E. This has got the full battery potential across it. So the current in case D is just going to be E over R. Current here, we're calling this E. 2 resistors in series, so the drop over this top one is going to be E over 2. My current for case E is going to be E over 2R. And then my final case here, I don't have a resistor in series with my point of interest, but I do have the battery. So here I'm going to be finding the battery current, and that is going to be the battery over the equivalent resistance. And in this case, you can see that the equivalent resistance is going to be R over 2. So my battery current is going to be 2E over R. And that's the same as the current for point F there. Okay, so what does that give me for ranking? I'm going to change up my color here. For ranking, that gives me, which one is the greatest then? B at 2E over R, and that's equal to F. And then what do we have next? A and D at E over R. And then case C is next at 2/3. And then case E is last at 1/2 there. Okay. So again, there are different ways to look at this. You just want to make sure that you have a consistent way that is at the same time that you're figuring out what the numbers are and stuff, that you have a conceptual connection with what you're doing. Okay, so this is again kind of the same circuits here. And what they're asking us now, though, is they're asking us for, it's kind of interesting question, rank the voltage at the upper right-hand corner relative to ground. So that just means that basically the elevation, right, the potential at these upper right-hand corners here relative to, this is the symbol for ground here, basically the upper right-hand corner relative to the lower left-hand corner. So if you had a voltmeter, those are just simply the 2 points that you would be connecting your probes to. And when you're thinking about this elevation-wise, which you should be, you're looking for the height difference there. What is the difference in elevation between those 2 points? Basically between the negative terminal of the battery and the upper right-hand corner of each circuit. So let's go through here. We can do this one. You can do it symbolically. You can do it numerically. It doesn't matter. I want to kind of speed up a little bit. So I'll keep these in terms of numbers, and I would challenge you to go back and do them symbolically. So if this is 12 volts here, I know that I'm dropping, these 2 resistors are each going to drop 6 volts, right? So if I call my ground here 0, right, that's 0 volts, then I'm up at 12, like say right here. I drop 6, so that means this point here is at 6 volts. Going on to case B, the negative terminal of the battery is the place that I'm always going to be calling my 0 volts. And that's what they mean when they're calling that ground, is they're just saying this is the lowest or this point is the point we're using as the lowest elevation in our circuit, right? Structurally, it is the lowest, so we're going to call that ground. I don't use the ground symbol a lot, partly because I want you to not rely on it a lot. I want you to be able to figure out your way around a circuit, the circuit architecture, without all that. Okay, cool. So from if I move up from ground, I go through the battery. So I'm going up 12 volts. And then if I shift to the right to point B, I'm still at 12 volts. So this here is still up at 12 volts of elevation. I haven't moved. I haven't descended. I haven't gone through any resistors or anything. Case C, again, we're starting at 0. I go up through the battery, so I climb 12. Remember that each of these resistors is a drop of 4 volts, right? So if I climb 12 to here, and then I go down 4 volts to here, that leaves me with 8 volts at this upper right-hand corner. It's 12 minus 4, leaves me with 8. All right, going on to D, 0 volts. Again, I climb 6 volts as I go up through the battery, and then as I go from the positive terminal of the battery to point D, I don't go up or down at all. Wires themselves do not change electric potential. You don't change any elevation. There's no energy coming in or out of the circuit there. And again, what we do is we're just considering negligible resistance for our wires here. It's intro class. It's the best way for us to do it. So we're still at 6 volts up there. Case E, I'm down at 0 volts, the negative terminal of the battery. Go up the battery. Remember, each of these resistors drops 3 volts. They're in series, they're identical resistors. So I'm at 6 volts here. I drop 3 volts. So here I'm at 3 volts. And now finally here, 0 volts. I go up through the battery. I'm at 6 volts here. And as I go over to F, I don't cross through anything else. So I'm still at 6 volts. That hasn't changed. Okay. So now I'll rank this. The highest one looks like that 12 volts, case B. And what else comes next? C at 8 volts. And then it looks like A, D, and F are all at 6. And then case E is 3 volts. I'm going to check my answer real quick before moving on. Okay. So this, of all the skills we're doing, this one, I got to say, this one right here, where you're mapping out, you're finding the different elevations and you're sort of seeing how they relate to each other. This is the money skill right here. Okay. Moving on. So this again is current upper right-hand corner. We already went through the one above. I don't think that you need me to walk you through this one. This one should be, the idea here is that the student has gained the skills to be able to kind of fly through this one here. And what I would encourage you to do for each of these is go through and actually calculate, like we did above, calculate the currents for each of those. And the ranking you should get here is C is greatest, B and E are the same, and then A, D, F here. Okay, and then finally we come to this one here, bulb brightness. And working through here, most of these are fairly straightforward, and students tend to do fairly well on these. Here you're going from brightest to dimmest. And for this first one, number 1 here, they're just trying to see if you're fooled by the position of the bulb, right? In general, in my class, students are not. So in general, we see that here they're all equal. I'm just going to throw in an equal sign to designate that. They all would have a potential difference E. If you, for the justification here, is that in all cases, the potential across bulb X or whatever is equal to E in all cases. So that would be equal. So you're looking at potential difference here. You might say, well, I really like to look at current, and a lot of students that have had circuits before are very like current centric. And I'm going to constantly try to pull you back from that. And what I want to do, I mean, potential is definitely the more fundamental quantity, and I'll show that to you over and over again. You don't have current unless you have a potential difference. It's not the other way around. You don't have current unless you have a potential difference. So it is much more powerful to be able to look at a circuit and map out where the potential differences are, because that shows you really like the actual architecture of the circuit and where the currents might or might not be, and how you can control the currents, which is the point, right? How you can control the currents through potential difference. Okay, moving on to number 2 here. So again, I'll look at potential difference here. I've got the whole battery across that bulb. Here I've got half the potential, and here I've got a third of the potential across there. So I can know right away that my brightest bulb is going to be A, followed by B, followed by C. So remember too that when we talk about electric potential, that quantity is equal to electric potential energy per unit charge. So we are talking about energy, and that's what's represented by the brightness of the bulb as well. Okay, case 3 here. In each of these cases, we're going to have potential is going to be equal to E over 3. They're just seeing if they can fool you again by position of the bulb. A common misconception students have early on is that current is a quantity that gets, quote, used up in a circuit, which is a huge misconception, and something that can, a kind of a confusion that can come about by looking at current. Whereas if you look at potential, it can kind of clear up some of those things. So here we see that they're all equal. They're all equal to E over 3. Case 4, here again, look at potential difference. If I look at case A, they're kind of trying to fool me by having this wire bend a little bit. But this has a potential difference of 2E across it. So you've got two batteries in parallel. Two batteries in series here. So they're made to kind of look like as though they're in parallel, but they're actually in series. So you have 2E. In case B, you have two batteries and they are in parallel. So here you only have potential difference E over your bulb. Case C, you also have potential difference E there. So your brightest would be A, and then B and C would both be about half as bright as A and equal to one another. So case 5 is definitely the most interesting case. If you haven't already spent a bunch of time on this, I hope you have, then just pause the video right now and do your best to come up with some kind of logical answer before you watch me like give this away. But the process that I'm going to put out here right now for you as you're analyzing this process wise, I'm going to use a highlighter in some different colors. So let's use a fairly thin highlighter if we can. And I'm just going to go in each of these cases, and the positive terminal of the battery, I'm going to highlight everything that's connected to the positive terminal of the battery with this kind of red color. Okay, now I'm going to go change my color to blue. I'm going to highlight everything that's connected to the negative terminal. Remember, these batteries are all the same. The negative terminal of the batteries with blue. Maybe you can see where I'm going with this. So right away, let's pause here and see what we see. So right away, we see that in case A, it's really clear that this bulb here, bulb X in case A, has a potential difference E across it. It goes from red to blue, which is what the battery does. Another thing that we might notice about case A is that these two bulbs here don't light. There's no potential difference across these two. So I could take my blue highlighter and just highlight all through that section right there. So just because there's a bulb sitting in a circuit does not mean that bulb is always on. We have switches, circuits. When we build circuits, we build them to do things and to generally exist in different states for different reasons. It's that kind of control that we want. Okay, if I look at case B, then that kind of might give away some of what's going on with case B. I see that this bulb here, my bulb of interest, isn't going to light up at all. that there's no potential difference across it. And if there's no potential difference across it, then it's not going to light up. And I have a potential difference of 0 across that bulb. Case C, well, there's something else going on here. I need a third color. For case C, there are more than 2 values of potential. There are more than 2 elevations. So if I start from the positive terminal of the battery, I'm up at E. I go through this bulb, and then I have this third color. I'm first just going to highlight in green this little pathway right there. So the bulb on the left and right are going to light up. This top bulb has no potential difference across it, so I'll just color right through it. So that top bulb will not light there. And what that tells me about the bulb of interest is that it's wired in series with another bulb to the battery, and the potential difference across that then is going to be E over 2. So I'm just going to go back through real quick and cross out the bulbs that would not be lit at all. So that bulb would be dark. These 2 bulbs would be dark. Again, no potential difference across them. And these 2 bulbs would be dark. No potential difference. So notice the bulb is wired. It's got wires on both sides of it. It's in the circuit. But unless there's a potential difference across it, it will not light up. And what that means is that there's no current going through that bulb, right? So current happens only when you have potential difference. Cool. So that gives us our ranking. A is going to be the brightest. C will be about half as bright, and bulb B will be completely off.